In this video, we're going to look at an exam question from the engineering unit to do with the mechanics part of the unit. Pause the video now and try all parts of the question. So 3AI, show that the maximum angular speed is 0.03 radians per second. So this is potentially a tricky question. We need to use this graph, and we also need to use the information given in the question as well. So we've been given a speed versus time graph. So what does the area under the graph equal? The area under the graph equals the displacements, the angular displacements. So therefore, the area under the graph is going to be equal to pi over 2. Why is it pi over 2? Well, that corresponds to 90 degrees, which is how far in angle that the bridge has actually turned from closed in this position along this axis to open in this position. So that's obviously 90 degrees. So what is the area under the graph? Well, we've got the area of two triangles and a rectangle, which for me is the easiest way to think of this. So 0.5 times by 25 times by omega max plus the rectangle, which again is 25 times by omega max. It might help just to put some brackets here, just so we don't make a mistake. Oops, not equals, plus the area of the final triangle, which is 30 times by half, or 0.5 times by omega max. So now we're solving this equation. And once you solve this equation, you get 52.5 over 1.57. No, sorry, you don't. If you solve this equation, you've got 1.57 over 52.5 equals omega max, and then that will obviously work out to equal this. Calculate the angular acceleration of the bridge in the first 25 seconds. So angular acceleration is the change in omega over the change in time. So this is really easy, 0.03 radians per second over 25 seconds, which will give us the angular acceleration, which is 1.2 times 10 to the minus 3 radians per second squared. Part B. Calculate the torque that must be applied by the driving motor to give this angular acceleration. So we've been given in the question, we've been given the moment of inertia, I, and we've been given the frictional torque. Sorry, the constant frictional torque, sorry. So what do we need to relate? So we need the torque from the motor, which is obviously going to encompass this frictional torque, and that is going to be equal to I alpha. So I is the moment of inertia, and we've been given angular acceleration in the previous question. So it's just simply a case of plugging in those two numbers, which is 9.1 times 10 to the 8 times by angular acceleration, and that will give us 1.4 times 10 to the 6 Newton meters. The power output of the driving motor to keep the bridge moving at a constant angular speed. So the clue is constant angular speed here. So now we can use the formula that people forget all the time. Power is torque times omega. So this is power is force times velocity if we're not talking about rotational systems. So the torque, so now we need to be careful with the torque. It's moving at a constant angular speed, like I highlighted. So this is where we use the frictional torque, because if it's moving at a constant velocity, then there is no resultant force. So the power of the motor is only overcoming the friction. So 3.5 times 10 to the 5 times by the angular velocity, which is obviously this bit here when it's moving at a constant velocity. so 0.03 radians per second, and that will give us 10.5 kilowatts. Finally, the maximum kinetic energy of the bridge. So this is really easy. Kinetic energy is 0.5 I omega squared. We know what omega is, we know what I is, plug in the numbers, and you get 4.1 times 10 to the 5 joules.